Students, welcome to part 3 of elementary particle physics. We have been looking at the 4 fundamental interactions in nature, the 4 fundamental forces which can act on elementary particles. They were the electromagnetic, the strong nuclear force, the weak nuclear force, and the gravitational force. Now, before going to explain about the force at a distance, I would like to show you what they are. We know that gravity acts on mass and energy, electromagnetism acts on electric charges, strong interaction acts between a proton and a neutron. That means it keeps a proton and a neutron. Till now we have not learned about quarks, so I will not talk about it. And weak interaction is the interaction between subatomic particles that causes radioactive decay. So that much it's enough for us to learn for the time being. Now what I was about to explain in the part 2 towards the end is that we know that since the action of one body on another body was earlier thought that this body can push this only by physical contact between the both of them, but then gravitational force and electrostatic force, it gave the idea that no, this can happen even without bodily contact. Just as a body is attracted due to the presence of its mass by the gravitational force or the electrostatic force acting on charged and uncharged particles in different ways, which happens without contact between the force, the idea of exchange particle came up. And what this is, we'll look at it in a very simple way. You see, electromagnetic field, quantum field theory was electromagnetic interaction or electromagnetic force was studied in field theory. According to which it was assumed that a charged particle, it modifies the space around it, which we call field, isn't it? We say the electric field due to that means the space surrounding this charge has been, and we know it. So it modifies the space, and so when it attracts another, suppose either a negative or a positive charge, the interaction happens between these two by the exchange of a photon. Now it may sound very strange to you. For you it is enough to know that this is a finding of the field theory of electromagnetic force. So and it is an accepted theory, and so we will accept it that yes, electromagnetic interactions, there is a exchange of a particle, and so from this the particle exchange, the idea of an exchange particle came into the domain of elementary particle physics or physics. So we now know that yes, for electromagnetic field theory, for electromagnetic force, there is a particle that is exchanged, and that is a photon. Now it is different that this photon has got characteristics which are very different from light photons which are present in a stream of light, where photons are energy packets, as we know. Here photon means these photons has got a special name. They are called virtual photons, and what these qualities, for what qualities they have, they are called virtual photons. We will not go into this. You will be learning these things in your postgraduate classes. For your undergraduate classes, it is enough for you to know that in case of EM interactions, since now we have learned 4 types of interactions, for electromagnetic interaction, it happens to the exchange of a particle called photon, our well-known photon. And basing on this electromagnetic theory, field theory, we know there is a meson theory which was given by Yukawa, and perhaps I must have mentioned it to you in some of your earlier classes. So according to Yukawa's meson theory, in the interaction between a proton in a neutron, or a proton and another proton, or a neutron and a neutron, these interactions also happen through exchange. And in this case, the exchange that happens, what particle is exchanged? That particle is the pion. So for electromagnetic force, the exchange particle is photon. For strong nuclear force, the particle is pion. And for weak interaction, there is another particle called the the W boson, like this. So these are accepted facts, and it has been proved to be true. Now what happens in case of gravitation? Now this is the only point where this exchange force thing is not working. Till now it has not been found, but it has been assumed that yes, if these three forces, electromagnetic, strong and weak, are possible through exchange of a particle, definitely there must also be another particle associated with gravitational interaction, and they have named that particle as graviton. Till now graviton has not yet been discovered, but then most of the particles are being discovered, and as elementary particles physics is progressing, scientists are very optimistic that graviton also will be discovered. Now perhaps we will understand what we mean by these particles. Now we go back to our original discussion about the elementary particles and these forces and all these things. So because you see, look at this this slide, fundamental interactions between elementary particles. See, this particular chart is very important for examination point of view. You see here there is a comparison between the four fundamental interactions. We have the strong interaction. If I take it first, let's look at the last column, exchange particles. For strong interactions we have pions. For electromagnetic we have photons. For weak we have got W and Z bosons, which are some new kind of particles. And for gravitations, the yet not found particle is known as graviton. Now there you see there is a relative strength can also be seen from here in the second column. You see, if strong force we take it as 1, electromagnetic is 10 to the power minus 1. Let's see, pi minus 5, this has come on my slide as a mistake, this shouldn't be here. And then weak is 10 to the power minus 13, and gravitational is, you see, it is even weaker than the weak, but its gravitational is 10 to the power minus 37, so strength is the lowest. Then why do we call it weak, 10 to the power minus 13? Because it's a type of nuclear physics which is much weaker than the strong nuclear force. Then the ranges are also given in the third column. And now we move on to like this. I have put an asterisk on pion. So for strong interactions we had written that the exchange particle is pion, and this is before we go to the strong interaction. That means before we go to the standard model. See students, till now whatever classification of elementary particles we are studying, it is not based on the standard model, it is the model before the standard model. Till then the quark was not discovered actually. So till then this picture will do. But after quark, you see, In quark model, exchange particle has got a different type of exchange particle. It's called the gluon, which we will come to know in a few moments. See the fundamental force. This is a diagram explaining, not explaining actually, depicting the four types of fundamental forces. Then strong has got these qualities. You can see, please note down these things. I am not going to explain this. And okay, then all physical processes satisfy laws of conservation of. Yes, this is very important because this is something that is usually asked in the examination. All physical processes, we know that all physical processes satisfy law of conservation of energy, momentum, linear and angular, and charge. But there are certain additional conservation laws which are followed by some of the elementary particle interactions, which means what? All physical processes, when I said all physical processes means I meant all the four interactions. But here are certain others. You see, this chart is also very important. Like, look at this parity. We have learned about parity slightly in our first unit. What is parity? There's every particle has got parity associated with. So parity is conserved in strong and electromagnetic. Now what is baryon number? That is something we have to see. What is lepton number? Isospin we had already seen. Strangeness we know. Charge and time reversal and all this we don't know. Now what is baryon number? Baryon number is a number associated with all baryons. For all baryons, do you remember what was baryon? In fermions we had two types of particles. One were the leptons and other were the baryons. Baryons are the heavy fermions. So baryons, all baryons have got a baryon number B, which is equal to 1, and for non-baryons it is equal to 0, and for all antibaryons it is -1. So when I say antibaryons, you might have a problem because you see a proton has a baryon number B is for a proton B is equal to 1, but for an antiproton B is equal to -1. What about an electron? Electron B is equal to 0 because electron is not a baryon. So that is about baryon number. Now what about lepton? Lepton is the same story. For leptons it has got a value of 1, and for non-leptons it has got a value of 0. For anti-leptons it has a value of -1. So electron, which is a negative, it's a particle, so for it L is equal to, I forgot to tell you that baryon number is denoted by B and lepton number by L. So L is equal to 1, and for E plus, what is E plus? Sorry, this shouldn't be a minus. Yeah, E plus is a positron, and for it L is equal to -1. And what about a neutron? For neutron L is equal to 0 because neutron is not a proton. Isospin we had already seen. Isospin, proton has got a isospin of half, neutron has got a isospin of -half, and pions have got isospin 1 for +1, for pi minus it is -1, pi 0 it is 0. So you don't have to remember all these values. I thought I'll just introduce these to it. Strangeness we have already seen. Strangeness is the different strange particles have got different values of strangeness, which is denoted by capital S. Charge, parity, time reversal, these are things that you actually don't need to know now, but these are certain conservation laws. That means before and after the reaction these things have to be conserved. So I'll stop this part 3 of today's class.